In Chapter 4, we learned to write the chemical potential mu sub J for a solute J in solution in terms of mu J0, a standard chemical potential for J, and in terms of A sub J, the activity of solute J. If the solution is ideal dilute, in the sense that the solute obeys Henry's law, then we can express its activity A sub J as the ratio of the molality B sub J to the standard molality B0, where B0 is equal to 1 mole of solute per kilogram of solvent. Recall that the activity must be unitless. So if the solute J obeys Henry's law, we write its chemical potential, mu J, as mu J0 plus RT natural log of Bj over B0. In Chapter 4, we also developed an expression for the chemical potential of a solute in a non-ideal solution, where the solute obeys neither Henry's law nor Raoult's law. In this case, the activity of solute J is expressed in terms of Bj, the molality of solute J, B0, the standard molality, and gamma J, the activity coefficient for solute J. The chemical potential for the solute is then written as mu J0 plus RT natural log of gamma J, Bj divided by B0. Finally, we need to remember that if we deal with extremely dilute solution, that is, with solutions where the solute molality approaches 0, then the solute obeys approximately Henry's law, and the activity coefficient approaches 1. For a solute that is sufficiently volatile that you can measure its vapor pressure above the solution, the solute activity coefficient can be obtained by comparing the actual vapor pressure of the solute above the solution to the solute vapor pressure predicted by Henry's law. However, this approach will not be appropriate for ionic solutes in aqueous solutions, as ions are non-volatile and Henry's law is not applicable for such solutes. Hence, another method will be needed for the estimation of the activity coefficients. Electrolytes and non-electrolytes also differ in the nature of their interactions. Non-electrolytes are neutral species and interact through van der Waals forces. Depending on whether or not hydrogen bonding or dipole-dipole interactions are involved, these interactions are typically significant only over short to intermediate distances, let us say distances equivalent to a few molecular diameters. At sufficiently low concentration, non-electrolyte species are sufficiently far from one another in solution that they do not interact with one another. They only interact with the solvent. The situation is quite different with solutes that are electrolytes, as these species interact through Coulombic forces. Such forces are much longer range than van der Waals interactions. Even for very dilute solutions of electrolytes, interactions remain significant between electrolytes in solution. To get a feel for the average distance between solute molecules or ions in solution for different solute concentration, examine the following table. This table shows that for a solute concentration of 0.001 mole per liter, solute molecules or ions are separated by about 10 nanometers, the distance needed to fit about 40 water molecules. Under such conditions, the interactions between non-electrolytes would be very weak. However, at that same concentration, the interactions between ions would be very strong, and significant deviations from the ideal dilute solution behavior would be expected. Please note that there are some errors in the corresponding table in your book.